Okay, good afternoon to all. We are now in this second day of this afternoon session lectures. Uh, in this lecture, I am going to introduce these combustion reactive systems, where we'll try to uh, introduce other conceptual reactions which we normally and call them as elementary reactions, global reactions. So elementary reactions are basically those reactions that are formed during the species formations, and global reaction that you see when the reaction gets completed as a whole. So that global reactions we in our previous lecture we dealt with, either it can be a lean mixture or rich mixture, in which you will find either CO or NO if, or excess oxygen depending on the mixture composition. This is one part of the analysis. Then other part of the analysis is we will try to introduce this reaction mechanisms. So reaction mechanism which takes care that for this formation of elementary and global reactions, we want to see that what are the possible ways, depending on the pressure and temperature ambience condition in the reactor, what are the possible ways different species are formed. So in a certain situation, whether it is a favorable conditions for CO or NO, so that way based on this reaction proceeds. In some cases these reactions are either chain reaction or chain it gets also branched, so chain branching reactions. Next important point is chemical time scale. If you look at the instantaneous, let's say ignition, so ignition event lasts for about maybe nanosecond or maybe micro or nanosecond range. So in that ignition period, uh, the combustion takes place. That means entire duration of combustion, if you to take starting from fuel and air, when you start, ignition starts, all of a sudden we see the products as a whole, which is combustion products. But in between these two, formation of uh, products, how fast it forms. So what is the reaction time? So one is the chemical time scale in which reaction gets over, fuel air mixture combustion reaction is over. Other is chemical time scale of those species formation. You can imagine if it is a long, it involves many number of elementary reactions and many global reactions to come out a typical time scale. That typical time scale is almost close to microseconds or still further less. So there are some categorically we call this chemical time scale with certain definition. Then coupling reactions means uh, there are different ways we can model these reaction systems, and some of the reactions can be I mean, when you try to this when you talk about this coupling reaction systems, it is basically to analyze thermodynamic concepts how you are going to introduce for this reaction analysis. One such model is constant pressure fixed mass reactor. uh, Other is constant volume based fixed mass reactor, well starred reactor, that means it's a kind of a steady state mixing reactor. Plug flow reactor, it is something like it's a, when the flow is taking place in a duct, flow is moving, at the same time we introduce fuel during the motion of the oxidizer or air. So those analytical concepts are uh, um, are introduced here to talk about coupling reaction systems. But before you start all these things, the first point that I need to discuss is the Fick's law of diffusion, because uh, because that is the basic law that governs the mixing systems. So in a combustion process, why this Fick's law of diffusion is important? Because it involves chemical kinetics, short duration phenomena or event that is going to happen. Second, to analyze the chemical reaction rate, and of course during this thing, in addition to the heat transfer, there are also the concept of mass transfer, because normally in the thermodynamic analysis systems, we have a fixed mass system or variable mass systems, but here additionally when species are formed, one species try to diffuse into others. What is the, I mean, how fast it can diffuse? So diffusion is just a concept that there is a perfume bottle is one corner of the room, but we can smell at every parts of that room, which means there are some mechanism mass transfer takes place from one end to other, and that concept we call as a diffusion. In this case, uh, the 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 chemicals inside the perfume bottles tries to diffuse in the air. See, that means one gas tries to diffuse into other. So the possibilities, there are concept like we can have two species kind of diffusion. We can say we are trying to diffuse nitrogen into oxygen, oxygen into argon. There are so many possibilities. When this diffusion takes place, it takes care about the I mean how fast we are getting that effect is mainly based on the diffusion coefficient, and a diffusion coefficient is different for uh, different gases, and some of the things we call them as a binary diffusion coefficients. So that is the basics of Fick's law of diffusion, which talks about two things. One is mass transfer, other is there are possibilities that heat and momentum transfer can take place. So mass, heat and momentum transfer will give you the complete spectrum analysis for the reaction systems. To do that analysis, mainly the mass transfer rate law for reacting gas mixtures is governed by Fick's law of diffusion. So here the importance of Fick's law of diffusion we are trying to explain here. Uh, when you try to see conventional mass balance equation, and this Fick's law of diffusion is basically uh, during a combustion reactions, some species are formed, some species disappears, so many permutation combination is done. Through this process, the main mass, the conventional mass balance equations gets modified. So those modifications are introduced because there are two things we are going to see for mass conservation. One is mass, other is also species. Species also forms and disappears, but that identity of the species has to be there throughout. So first thing is that we define this Fick's law in a manner that it says that if there are two species, basically here we are talking about this binary diffusion coefficients in which we talk about diffusional fluxes. The flux is nothing but what you are calculating the mass flux with respect to unit area perpendicular to the flow. So, if there are two species A and B, we are trying to define a term mass flux of species A per unit area perpendicular to flow, mass flux species for species B, which is again defined perpendicular to the flow, and adding these two will give you the total mass flux of the mixture. But means that when you talk about its density, it is a global density of the mixture. Now, once you know this mass flux value, we can easily define mass fraction, and this mass fractions in terms of Ya and Yb. And in addition to that, there are two parameters we are going to define. One is that is binary diffusivity term. This is something like thermal diffusivity what you use in the heat transfer, similar to that. Its unit is meter square per second. So, if you look at this equation, this is something similar to heat transfer equations or Fourier's law of heat conductions. So, that there, but here we are through that modeling, we arrive at the term this binary diffusivity term. There are two things, one is DAB and DBA. Identically they are not equal because the tendency of species A into B or B into A, it all depends on its own intensity. So, that way the terms can be values may be different, first thing. Second thing, there could be possibility of sign, it may be which depends on the concentration gradient, that can be positive or negative. So, that way we can find out this, we can simplify that equation in this term, and in this, through this term we started with this mass balance equation, but ultimately we are going to arrive at another equation which is called as diffusional flux equations that introduces these two terms. The same mass flux species, this is the mass flux, but this is the diffusion flux, that comes due to the concentration gradient, and it is nothing but a function of density, which is a mixture, and binary diffusion coefficients for if it is A to B or B to A. So, these equations gets further simplified, and if you try to make an analogy between Fourier's law of heat conduction equation and diffusional flux equation, that means we start with a fixed law, and this fixed law gives another equation which is the diffusion flux equation, and this diffusion flux equation has some analogy or bearing with the heat conduction equation. If you try to compare heat conduction equations to these things, the terms are similar, and also since heat transfer always takes place from high to low, so there is always a negative sign here, and here also higher concentration to lower concentration, and with some mathematical combinations, ultimately what we will end up is that when you say total mass is conserved, here also it gives another equation is total diffusion flux masses is also conserved, and this equation is always valid. So, when we talk about combustion equations for conservation of mass, one is we have to also say that diffusion flux equation also gets satisfied, which means total amount of species that are formed also nullifies the what is goes out. So, through this there are what I have told in these last previous slides, they are based on the mass flux observations. One can also think of the Fick's law in terms of the molar analysis, where and there we call as a molar flux. What remains same, instead of mass kg we are talking in terms of kilomole or mole, and equations remains same. Then we enter into the next step, that what is called as reaction mechanisms. There are two types of reactions which were maybe Sarah has also introduced. What is one is global reactions, other is the elementary reactions. First part is the global reaction, and global reaction means if you start the basic things like we have fuel, oxidizer, they give the combustion products. And when you talk about the chemical kinetics, we are more interested that what is the rate at which the fuel is consumed. And the fuel is consumed, which means that concentration of fuel, because since it is consumed there is a negative sign here, so its composition comes down. So this is the equation, rate chemical kinetic equations, that how the fuel gets consumed. So here that equations is normally expressed in this form. Here we introduce one term what is called as global rate coefficient Kg, which is a function of temperature. And one thing you notice that the concentration of fuel drops and oxidizer also drops, and there with this concentration raised to the power exponent gives the rate at which the fuel gets consumed. And the one thing to be noticed here, the when you say second order, third order things, M and N, they relate the order of reactions. How do you decide the order? If the reaction is of nth order with respect to fuel, mth order with respect to oxidizer, mth order with respect to oxidizer, nth order with respect to fuel, then the overall reaction will have n plus m. So just add 2 plus 3, 3 plus 2, it's a fifth order reaction, second order reaction, first order reactions. So that way we make a judgment what is the order of reactions. Then we will try to move on to the elementary reactions. So elementary reactions, like we normally do not see these reactions when the equilibrium takes place. We start with a global reaction with this. We are more bothered about in this case hydrogen and oxygen gives water, and this water formation we are interested, we call this global reaction. And through this process, through this formation of water, there could be many possibilities among the combination of, since it is a very simple one, we can find one formation is like during this formation of water there is a possibility of a free radical hydrogen atom or any kind of arbitrary molecule that can form, but which is not visible, but that aim, so any arbitrary molecule would have formed, but somehow it gets consumed. So finally it doesn't show here. So there are many, and also we may have hydroxyl radicals, hydroperoxyl radicals. So these are kind of elementary reactions we don't observe. And imagine that all these reactions time scale is few milliseconds and a few microseconds, and during this microsecond we observe this reaction, but we don't see these formations. So entire chemical kinetics is governed by this what we call as reaction mechanisms. Now to analyze such reaction mechanisms, they are standardized in three categories. One is unimolecular reaction, bimolecular reaction, termomolecular reaction. That means two species, unimolecular, species A gives species B, then means a single reactants will give a single product, or a single reactant can give 2 or 3 products, that doesn't matter. But when you when if this is the case, we in this case this is mainly true when you talk about these elementary reactions. For example, O2 can O plus O can give you O2. Hydrogen can decompose to H plus H. So these are kind of things which is unimolecular. Bimolecular reaction means two species try to combine. So H2 plus O2 they can form this way, or H plus O2 they can form this way, OH plus H2 they can form this way. So there are many possibilities like this, and each of reactions will have some term associated with that, what is called as rate coefficient. So depending on unimolecular, bimolecular or thermomolecular reactions, we can find out the rate coefficient for each reactions. So this is actually required at the intermediate level, just to know how fast you are expecting the reaction to happen, and more or less this judgment is required that when a combustion takes place, to how much time it takes to go from flame mode to non-flame mode to detonation. All these things analysis is required. Another important significant of this chemistry is this Arrhenius equations. So this is a very standard equations that gives the overall picture, and this is mainly nothing but an experimental observations, and it has been found that this equations is true for mostly for bimolecular reactions. So based on this, with which it is standardized in this manner. So if it is a bimolecular reaction where A plus B gives C and D, so we can define this KBI, which is, we call this as rate coefficient. Now what is this rate coefficient? Possibilities that you can have to do some measurement in that scale, experimental observations. But what this Arrhenius equation, he proposed a model in which the KT was defined in this manner, in an exponential manner. The rate coefficient, he proposed that rate coefficient only mostly depends on the temperature. Because the reaction ambience depends both pressure as well as temperature, but his proposal was that, let's say, the temperature dominance is more as compared to pressure. So it is the temperature that normally governed, and this philosophy happens to be true for all types of combustion reactions, and with some experimental evidence. So normally when you say that temperature increases, your chemical kinetics changes. One particular temperature, oxygen start dissociates, nitrogen start dissociating. This is for air. So it's with this logic, the the Arrhenius equation was formed, and here the parameters that are of important is EA, which is the activation energy. A and B, there are some empirical parameters that govern at what equations we are looking at, and here we are going to use R bar, universal gas constant. And these activation energies for many standard reactions, already it has been tabulated for the activation energy. For example, for this kind of things, your activation energy you can find out this. So this is already noted in the data book. So accordingly one can take out, use these equations, and these equations remains valid although it is empirical. Now apart from this, we are now going to introduce another term that is called as equilibrium constants. So there we say it's a rate coefficients. Now we are going to introduce equilibrium constants. Now, to define this equilibrium constant, we take again similar type of bimolecular reactions, and here the reaction can happen in both the directions. A plus B can give C plus D and vice versa. So, it is a reversible reaction. So, for a reversible reactions to happen, what we see is that when the reaction is moving in forward direction, the concentration of A and B drops. So, accordingly the rate coefficient in the forward direction is negative. If same reaction goes in the reverse, it is positive, which essentially is that during a reaction some species are formed, but again they cannot remain in that stage because continuously, because temperature and pressure doesn't allow to react with other, they try to reverse back. So, those cases we may have, and one particular situation this equation can be modeled, that under equilibrium conditions we can use this particular concept that concentration of A with respect to time is 0. So, based on this we can frame a linear equations consisting of the concentration of each species with respect to the ratio of rate coefficients in the forward and backward directions. Now, next question, and since you say that for a given reaction this is again both are function of temperatures. So, people try to interpret in two ways, either as Kc or Kp. Kc and Kp, that means in one case we are saying that the reaction takes place at constant concentration or at constant pressure. So, that way we Kc and Kp are defined. So, either it can be Kc or Kp, and some situations you can observe that we will find the identical or similar range of values of Kp and Kc, and that is true mainly for bimolecular reactions. So, that is the one way we can say that for equilibrium constant for a bimolecular reaction can be found out by assuming whether we are getting it at a constant concentration or pressure. But in a reaction, maintaining pressure is a better solution because we can control it, but we cannot control the concentrations. So, most of the cases for practical utility, it is the constant pressure which is followed to find this equilibrium constant. Another kind of reaction mechanism, in many case we use this steady state approximations. So, what this steady state approximations is that during in some certain reactions we really do not bother about how the reaction moves forward or backward, but what we really bother about concentration of one particular species during a reaction. We many a times we really do not bother about intermediate phases, concentration change and all, but we really bother about one particular case. So, for example, if you for this reaction if you try to see that what is the rate of production of nitrogen atom by using that previous concepts, and the reaction proceeds in either way. So, that way first equation we can find out based on the rate coefficient, and when we have a steady state concentration of nitrogen, if this number turns out to be 0, this number turns out to be 0 with a steady state concentration, that is an approximation. So, we are not looking at the reaction formation at any timely event, we are looking at steady state concentration, means during a steady state what is the how fast the nitrogen drops instantaneous. Basically we are not really bothered about instantaneous changes. During certain time frame we are looking at what is the average concentration. So, that way this equation can be modeled in this manner. So we get steady state concentration of nitrogen. So instead of bothering dN by dt at every time instant, we are really bothered about what is dNSS, steady state concentration with time. So this is more easy way of handling these equations. Then we will try to move a kind of reactions, and most of the combustion reactions are chain reactions. So it's a very short duration events, and these are like chain reactions. They occur in many chemical processes, and another thing is that we also introduce the term which is called as a chain branching reaction. So it is often possible that concentration of one radical species can cause rapid formation of the products, which means that why we say chain reaction? Chain reaction means how fast the reaction proceeds. Why this reaction proceeds? Because of presence of certain maybe you can say it's radical. That radical actually accelerates the process. So through these things one can we call this as a chain reaction and this chain branching reaction. The analysis of these both the reactions becomes very vital to understand the combustion systems. To introduce some of the things like how we can say whether there is a chain reaction or chain branching reaction. So there are three basically category. If you have a global reaction in this manner, we can say when the pressure and temperature ambience is created, A2 tries to, some molecule is formed, A2 tries to mix with this and it tries to dissociate. Now why it dissociate? Because this M is there, otherwise it would not have dissociated. So this is a what you say chain which starts initiation. So when it initiates and finally when the chain has to be terminated, because once AB is formed, at that point AB is all of a sudden doesn't form. A becomes A2 becomes A plus A plus B2 can be AB plus B, maybe A2 plus B can have this, and each reaction will have different rate coefficients. And why it is initiated? Maybe presence of certain molecules, maybe it may be a radical or it may be a catalyst. So that way we interpret this radical concentration that rapidly proportional to the pressure and chain reaction of major products. Then we will try to introduce the term what is called as chemical time scale. So every event, every reaction takes place for certain duration. One event when you start it has to complete. So there is a duration for which we define the time scale. So with respect to these reaction mechanisms, the time scale duration is hardly within a milliseconds. This is quite clear when you think about the combustion process in engines. Now mathematically how do you interpret? So what we call this as chemical time scale is nothing but a characteristics time, chemical time, which is required for any species concentrations to fall from its initial value, to a value which is equal to 1 by E times its initial value. Okay, so if we try to interpret those things in this manner, we say that some species is concentration drops down with time, and how it drops down, it depends on its rate coefficient. Then further simplification, and if you integrate this equation, we write like this, and here we introduce a integration constant which is nothing but its initial concentration, and based on this we define a parameter which is called as a chemical time scale, such that the final when at any instant, if you multiply by with any instant, if you take this concentration value, when you multiply by its time scale and take the ratio with respect to its original concentration, you get a value of 1 by E. So this is the definition of this chemical time scale. So what it in other way, instead of rate coefficient, we chemical time scale for a reaction can be written in this manner. So this is a unimolecular reaction, one can have it. So there are expressions for chemical time scale for bimolecular reaction and thermomolecular reactions. So this is expressed in this manner. So one can use this as a concept to find out the chemical time scale for a reaction events. Then you look into these reaction systems or coupling. So by coupling, I mean that for a given reaction systems, in our previous study we talk about the thermodynamics of mixture. Then you introduced into the combustion systems, and that story doesn't end there, because that's a thermodynamic analysis of a chemical systems, but we have not introduced kinetics into that study. So although we take it as a because all those are steady state analysis, but this chemical kinetic event is not introduced. So when you try to do this study in a full-fledged manner, and what we call as a combustion modeling, so we have to introduce its chemical kinetics of a reaction, which is based on the standard equation of this, how the concentration of fuel drops depending on the order of reaction, and with respect to other terms, the calculation of flame temperature, adiabatic flame temperature, calculation of enthalpy of products, reactants. So that is when you couple these two equations to make a complete modeling, then that is called as coupling of reaction systems. So we introduced the Fick's law of diffusion for species equation. We introduce chemical kinetics of the reactions. Then we already previously studied how combustion thermodynamically, how we model the combustion systems. When we integrate everything together in a single domain and try to solve them simultaneously, we call this modeling to be coupled. So there are three ways that when you basically four mechanisms in which we analytically study the coupling of reaction systems. One is constant pressure fixed mass reactor. All these words comes from the thermodynamics: constant pressure based, constant volume based, and both are fixed mass reactor. And when you do this, and they are perfectly homogeneous reaction, then we have a well-stirred reactor, which is a steady state, steady flow and perfectly mixed. Then we have a concept of plug flow reactor systems, the steady state, steady flow with no axial mixing. So why such modeling is required? Normally, in my previous lectures, I told that a reaction is modeled in a reactor, and in that reactor, if you assume the mixture is perfectly mixed, homogeneous, and we are using this equation: temperature is a function of time, concentration is also changes with time, and it's a constant pressure based reactor, then we call this as a constant pressure fixed mass reactor. I think this would be P This is a constant pressure, fixed mass. This is a constant volume, V as a function of time. So the assumption lies here, whether pressure is constant or volume is constant. This is a one category which is normally done in most of the analysis. And there are some situations like which is called as well-starred reactor. Means we in a given systems the mixing takes place, fuel air mixing takes place within the reactor, but simultaneously the fuel or air getting fed from one end and products goes out. This is another kind of modeling which is called as well-starred reactor. And other is like in some cases like what we call as a plug flow reactor. Many times so this is something like a piston cylinder concept. It's a kind of open system analysis. In some cases we feel that your air is moving and fuel is being injected simultaneously. For example, it is air is flowing in a duct. We can imagine that we are injecting fluid circumferentially, which means which says that there is no axial mixing. At every location, some locations we can inject fuel, so it's a circumferential mixing. And first mixer is found with and we can put simultaneously mixer and it allows to flow through this. Such kind of duct flow analysis is mainly used for the high speed engines, something like where we use ramjet and scramjet concepts. Normally air enters in a duct intake, what we call as intake or duct, and then mixing takes place as and when the fuel is inserted into the duct circumferentially at various locations. So through this mixing we try to, during this mixing process we try to ignite. So depending on the nature of your combustion, we can model this coupling reaction in this manner. So we have coupling reactions, all the coupling reactions has to enter into one of the reactor modeling. Okay, so this is how we model the coupling reaction system. Next thing is if you go bit by bit into this modeling, it is for this we need to develop the governing equations for this constant pressure based fixed mass reactor, and by doing this and another point to be noted here that the combustion reactions are mostly exothermic. During these exothermic reactions, the temperature and volume will increase with time, and through these things we also look into the heat transfer. So main motive of this analysis for a constant pressure based fixed mass reactor, we need to find out at any instant of time, we are going to find out the temperature and species concentration. So these are some of the governing equations that we enter by mixing thermodynamics or first law and calculation of system enthalpy, and finally we arrive at an expressions which talks. Our main intention is that how we have to find out how temperature varies with time, one thing, and how concentration also varies with time, either for species and as well as for global. So these equations will let you know that in a chemical reaction how species evolution takes place. Ultimately the solution for this equation boils down to this particular expressions: concentration for any species I during a reaction and temperature with respect to time, and all these equation has to be, these two equations has to be solved simultaneously to arrive at the final conclusion. So, final conclusion I will, why I am saying, because as you see here, your thermodynamic equations are mixed with chemical kinetics, and those chemical kinetics means with respect to concentration, and when you because this, to model these concentrations we require the information of equilibrium constants. So those things are already introduced here to find these two important equations. In a similar way, we also boils down the constant pressure based fixed mass reactor. One thing is for how temperature changes with time and concentration changes with time. So, we are not going more into this. Then moving for the constant volume based fixed mass reactor. So, here we use the same equations, but with an assumption that because when you say constant volume, we are more interested with internal energy. That internal energy information we can get from enthalpy, as we did in the previous case. Enthalpy, which means it is a with constant pressure based analysis you find enthalpy, then introduce using this equation and arrive at the internal energy calculations. So, by doing so we have one equation how temperature changes with time, and then we have other equations how concentration changes with time. Of course, since it is a, and most of the cases what you see that when you do this constant volume based reactor, essentially speaking, that when in a reactor the constant volume modeling is very critical, because we do not know how, because since we are fixing volume constant, we do not know how fast or what is the magnitude of level pressure rises within that container. So, there is a chance of explosion. So, here the word explosion comes into picture. When we do analysis for explosion, analysis has to be with respect to constant volume, so that we are actually simulating a situation of explosion. So, there when you say explosion, what you are trying to say, you have to see how pressure varies with time. So, that equation again comes from your temperature calculations, and that enters here. So, this equation is application finds during an explosion process. So, this is some of the case study that which any one of the textbook talks about, many standard textbook talk about. What is that? Whatever I have explained mathematically, and if they are modeled in one particular case, which is a simulation of a constant volume fixed reactor model for SI engine, to predict the temperature and concentration history, rate of pressure rise, knocking behavior, that is for ethane air mixture. So, this can be done in this manner, that one thing is that you can see here how molar concentration changes with time. One thing we say, this side we have fuel, this side we have here we have fuel, and here we take about its scale change, and from this equation the rate of rise in the pressure with respect to time is modeled in this manner. This behavior is significant because although we really do not look into the chemical kinetic aspects of the reaction, but ultimately what you see during an experiment process for an SI engine experiments, we see in terms of how pressure rise with time, and which is a normal combustion, the curve should look like this. If it is a knocking cases, the curve gets an erratic behavior. So this, why it is this erratic behavior? We say that seeing this pressure trend, we say it's erratic and it tends to give you knocking. But why this knocking happens? This knocking happens because how the pressure variation takes place in that modeling, by using that modeling. In this case it's a constant volume based modeling. So this is how it gives you an indication that how you control your charge or fuel air charge or concentration such that you don't get out, we will get rid of this knocking behavior. So main intention of showing this graph is that all these graphs are not just like experimental observations. Background thing, there are some combustion modeling that happens and we can also model that behavior in this manner. There is another concept, is a well starred reactor, in which we talk which it's a complete open system. It's a very complicated systems which involves mass, mole fraction and enthalpy which is entering for a given system, and same amount also goes out. And during these things and the process we are looking at within this reactor, what is the global behavior of pressure, temperature and any species concentration or mole fraction. So this is the sum of the modeling in which we try to see here modeling requires the knowledge of your Fick's law, mass formation or mass of species I and mass as well as species formation. So through these things one can also infer the concentration of any given species and at its mole fraction. And ultimately we are interested for this kind of these things, we get it from mass balance. Another equation we can frame about the heat transfer balance, and here one thing what we are going to think is that a mean residence time of a gases in a reactor. So what it means is that we say that something comes in and something goes out. So any gas which is formed in this during the reaction process, what is the minimum time it stays here before it gets out? So that term is calculated by this number which is the global parameter of the mixture involving density and its velocity and mass flux. And density, we can find out your ideal gas equation with respect to this ideal gas equation, P molecular weights and RT. So in a plug flow reactor, I am not going into details there because that analysis is complicated and it's a very short duration time scale event, and in which the mixing as well as combustion takes place simultaneously. So in previous studies we first think about the here we whatever instant your fuel is injected here and those information and the information at this state. So those informations are completely different because of the formation of the analysis is based on flame and non-flame mode, diffusion flame mode. But here it is not that way, it is the formation of shock waves because of the flow of air which is entering into duct. So to give a global picture how a plug flow reactor analysis has to take place, one has to think about mass flux equation, we have to talk about species flux equations, energy equation and momentum equation. By studying these things in a complicated manner, we are trying to, of course the analytical modeling, all previous thermodynamics analysis will not work out. We also have to link to gas dynamics analysis into this. classical thermodynamics principle will not work here. We also have to talk about the effect of shock waves in terms of pressure, temperature rise into this reaction system. And you can see the kind of complexity of the equations, how the density changes with space. Space means different locations you have a different density. When a different density means flow is no longer incompressible, it is compressible. So also the temperature also changes with respect to time, that every locked location temperature also changes with time. So there is no point in doing it in analytical modeling unless and until one has to put frame the equations for a given for a particular situation case. So this is all about, I need to talk about this, and these are some sample problems based on our understanding today over these lectures. One case we talk about ignition delay calculations in using these systems, well starred reactor systems. Okay, here we try to introduce a piston cylinder concepts to calculate mainly for this is normally standard equation, engine kinetic analysis for an for a IC engines, and in this engine kinematic analysis we are more interested that how your total volume changes with clearance volume, which is a function of compression ratio and other engine parameters. So that equations we are going to analyze here to calculate the ignition delay fuel cutoff studies. So these terms I will come back when you deal with the fuels, ignition delay and all these things. But what I am trying to say, the nomenclature, engine nomenclature has definite bearing in terms of the ignition and the calculation and thermodynamic analysis for the reaction systems. So with this I conclude. Thank you for your attention. Okay, sir.
So very good afternoon to all. So today I am going to talk about my PhD research topic actually, that was the film cooling system design. So these are the table of contents, like film cooling overview, then the history of the turbine blade cooling, and the cross flow overview, and the factors affecting the film cooling, followed by the experimental design, how to design the experimental setup for a film cooling application, then the numerical modeling approach for the film cooling problems and our key findings, and then the research publication we have in this area. So what exactly is film cooling and why we use film cooling? So component which is generally under the pathway of the hot flue gases, like the gas turbine blade and the afterburner of aero engine, and the nozzles which is generally subjected to the very high temperature, and to protect the component from the thermal stress, high thermal stress and failure, generally we eject a coolant through a surface hole, and which forms a thin protective layer over the surface and prevents the direct exposure from the hot flue gases. So generally the combustion product, in order to increase the thermal efficiency and power output, the temperature, inlet temperatures of the gas turbine have increased significantly over past few decades, and to protect the all components like combustion liner, the afterburner and the gas turbine blade, we eject a coolant through the surface. Coolant may be the air, may be the kerosene, or may be the any other fluid which is at relatively at a lower temperature. So this is the history of the turbine blade cooling. So early 1980, the metal temperature was not very high, so there was no need of the sophisticated cooling technique. And after 1970, the cooling technique, there is necessity of the cooling. So the film cooling and other cooling techniques, like first it was the other cooling technique like the regenerative cooling and other cooling conventional cooling techniques were evolved, and nowadays the film cooling, among all cooling methodologies, film cooling is the most commonly used technique to protect the metal from the hot flue gases. So the history of the film cooling was basically, the idea was generated in 1946 by Whitgard, which was basically used the in the high altitude the aircraft uh, facing the issue of the ice formation, and to melt the ice he suggested and to inject hot air and to melt the ice formation, and from there itself the idea of the film cooling was generated. And these are the common factors which affect the film cooling performance. So mainly we have the geometry related parameters like the shape of the hole, ejection of the secondary steam, so the angle at which the secondary steam is ejected with the main stream, and the shape of the hole also. So we have the different kind of holes, ejection holes, and the surface of the geometry, like it may be the aerofoil shape, maybe the corrugated or flat surface. Depending upon that, the stability of the film cooling depends. And the other parameters like the blowing ratio, so it is nothing but the mass flux of the secondary stream to the main stream, and then density ratio, which is basically the ratio of the secondary stream density to the mainstream density, and third parameter is the mainstream flow Reynolds number. Basically in practically it is the Reynolds number of the mainstream flow, or you can say the hot flue gas Reynolds number, and then the turbulence intensity. So these are the some common parameters which basically affect the film cooling performance. Apart from there, the other parameters also which on which the film cooling depends, but these are the common parameters. Next is the jet in cross flow. So jet in cross flow is closely related to the film cooling. So whenever a secondary steam enters into a cross flow region, so due to the pressure difference and combined effect of the pressure and shear, the secondary steam is basically splitted into the two rotating counter rotating vortex pairs, and that is commonly known as the kidney vortices. And that kidney vortices basically increase the mutual induction and causes the lift up of the coolant from the hot surface, and basically degrade the cooling performance. So with this cartoon one can see the number of vortices commonly generated for the jet in a cross flow. So the horseshoe vortices are basically generated in the nearby the secondary stream, and the wake vortices are basically in the wake region, which is initiated from the surface itself and extended up to the counter rotating vortex pair, and shear layer vortices are basically accompanying the counter rotating vortex. So these shear layer vortices and wake vortices are basically the unsteady vortices, and the counter rotating vortex pair and these horseshoe vortices are basically the steady vortices. So coolant ejections hole shape. So there are different holes were generated with the time passes. So initially the film cooling was started with the slot ejections, and but due to the slot there was a sufficient decrement in the material strength, and then it was preferred to introduce the cylindrical hole ejection. But as you can see in the previous slide, we have already shown that because of the mutual induction of the kidney vortices, there was a coolant lift off issue with the cylindrical hole. Then shaped hole was introduced by the Haven, and in case of the shaped hole, the hole is basically diverged in both lateral and the mainstream flow direction, and because of that the additional pair of the vortices are generating, and that vortices basically counters the effect of the kidney vortices. So basically the jet lift up is completely mitigated by the introduction of this shaped hole. And another way to mitigate the effect of the kidney vortices is the branching of the hole. So in case of branching, a main stream, a main hole, and side by side two branch of the additional holes. So the side holes also generate the vortices that nullifies the vortices formation in case of the cylindrical hole. And this is the setup, that is the setup I have designed during my PhD in NIT Manipur. So the setup consists of a subsonic wind tunnel facility, and there is a open circuit wind tunnel and the mainstream and secondary stream flow. So in case of the mainstream flow, the mainstream is basically a heated air, so we use the electrical heaters to heat the mainstream flow, and the flow straightener, by the flow straightener and through the test section mainstream will pass, and the through the pressure regulator mass flow controller, basically the secondary stream, which is as lower temperature, or you can say the ambient air, is supplied into the film cooling surface. So our study was mainly focused on the corrugated surface. So these are the common testing, means the blade can be used, any shape can be used for the film cooling, and the temperature profile can be recorded with the IR camera. So this is the picture of our setup actually. So this is the mass flow controller and the pressure regulator, and the setup was basically the insulated with the styrofoam and glass wall to maintain the uniform temperature throughout, because there was a temperature loss, and we have installed the electrical heaters also at the front of the uh, suction. And this is the calibration for curve for the boiling water for the IR camera. So IR camera was first calibrated with the thermocouple. So both readings, for to calibrate the IR camera we use a copper tank, and that copper tank basically painted with the matte finish black paint, and the IR camera was focused on the uh, one portion of the black finished copper tank, which is filled with the boiling water, and the water was boiled using the resistant heater, and the other side of the wall is temperature is measured basically by the thermocouple. So thermocouple was pasted, means fixed at the other side, and the one side temperature was measured by using the IR camera. So both the once the water was heated and they are allowed to cool the water, and with the passage of time the temperature was recorded through the IR camera as well as the thermocouples and plotted for the cooling of the water. And this is the comparison of the thermocouple measurement. So generally we calibrate the thermocouples reading with the IR camera before going to read the measurement of or take the measurement from the IR camera. So these are the position of the thermocouples. So near the hole region there is a high gradient of temperature, because main stream and both secondary stream are mixing. So main stream at high temperature and secondary stream at low temperature, so the temperature gradient will be high in near the just downstream of the secondary hole. So as we move on the downward direction, so secondary stream will be completely mixed up with the main stream. So accordingly the thermocouples are arranged in the downstream direction from the jet to the secondary stream to the further downstream directions. So just we have compared the measurement of the IR camera or IR camera and thermocouple measurement for the flat plate. And this is how we do the uncertainty analysis. So for a sample case we got the 12% of uncertainty, and this is just the this is basically the effectiveness formula, T main stream minus T wall temperature and T main stream minus T secondary temperature. So both main stream and secondary stream temperature we use to measure with the thermocouple, and the wall temperature we measure with the IR camera. So camera we use having the resolution of 320 by 240 pixels, and this is the uncertainty of the individual instrument, like flow uncertainty. So pitot tube, mass flow controller uncertainty, and the temperature uncertainty recorded by the IR camera and thermocouples are basically the 2 degree and 0.5 degree. This is the numerical modeling. So we have a lot of options for the numerical modeling, and we can use the right from the RANS model to the DNS model for modeling the film cooling problem based on the adaptability and accuracy required. So whenever we require for like vortices and other capturing of the other sophisticated flow physics, so we can go for the higher order turbulence model like LES or DNS or more unsteady RANS. But sometimes the domain size is bigger, so computational cost and the time will increase, so we prefer the RANS. So we have done in our study both, we have used RANS and LES both models. And this is the accuracy basically of the modeling approach. So once, if suppose we are using the DNS model, so it will resolve all the EDs, and if you are using the LES model, so it will only some extent of the EDs will be only means directly resolved, and some portion of the EDs will be basically the model. So for that we have the idea about the size of the vortices generated in the flow region. Based on that we can modify our mesh. So we basically prefer to find out first the size of the ED generated in our region or flow domain, and based on that we modify the mesh, and the mesh resolution basically we express in the non-dimensional Ward coordinates in all three directions, and we have the comparison given with the others study also, kind of similar study in the LES. And this is the symbol of the mesh we are using, and we have done the grid test. This is the structure maps basically generated in the ICM, and this is the way we calculate the grid uncertainty. So if we have a refinement factor like R21, like grid 2 or grid 1, there is two different grid, so we have the some refinement factor, and based on that we will find the grid sensitivity index like GCI based on the apparent order of accuracy. This is our key findings, like the in the first, this is our one of the LES study we did. So this is the one node below the cross flow region. We have taken a section, and this is the forward and reverse ejection basically comparison with the forward cylindrical and shaped hole. So in both the cases we can see that directly there is, this is the average contour taken by the numerical study using the LES model, and you can see the completely in case of reverse ejection the velocity field is completely shifted to the rear end, or you can say the trailing edge side of the flow. And another study, one of our study was related to the slot ejection. So that was basically to check the whether we are ejecting the locations, different locations, so what will be the impact on the flow stability, or you can say the film cooling performance. So we use different locations like L0, L25. So these are the different possible locations we have chosen, and based on that we find out the film cooling performance. So these are the different, because these corrugated surfaces are highly used in the afterburner of aero engines. So, and during some specific situations like combat takeoff and takeoff from the short runway, basically the extra amount of fuel is burned in the afterburner, which is generally situated at a rear end of the aircraft. So in that condition, due to the burning of the extra fuel, there is a significant rise in the temperature in the afterburner section, that around 200 to 300 Kelvin. So that causes basically, that requires basically a thermal protection, so their film cooling can be applied. So with that aim we have taken a corrugated surface for the investigation, and different locations or different combination of the holes we have used. And this is this is RANS based study, basically experimental and RANS based study. So these are the vortices which is generated. So once we are changing the location, so the vortices formations, or you can say the reed circulation, is also changing, and that causes basically the mixing of the, so our desire is that the secondary stream least mix with the main stream. So once it will mix with the main stream, it will not protect the surface. And this is the another study that we have done, basically that is the corrugated sinusoidal corrugated surface and the forward and using the reverse ejections. So that was also experimental and numerical study, and this is the result of a experiment numerical study. You can see in the forward ejection also, you can see the kidney vortices are forming in a plane perpendicular to the mainstream, and which is completely mitigated with the reverse ejection. And you can see the vortices are in planar, some kind of vortices you can see, that is the planar vortices which are generating basically in the plane of the corrugated wall, and the vortices are absent in the wall normal direction. And based on the temperature profile or thermal protection we are getting through this film cooling analysis, we have done the thermal stress calculation also, and because of the reverse ejection is better as compared to the forward ejection, both on the flat surface also as well as the corrugated surface also. So there is a significant reduction in the thermal stress can be seen. And these are the publication we have done in this area. And these are the work of my PhD thesis and master thesis, both were basically on the film cooling area, and presently I am planning to work in the multi-phase flow heat transfer, fluid surface interaction and combustion. Actually we have not done the experiment on the blood, we have done on the flat and corrugated surface only. No, in experimental we have shown the possibility actually in the back slide. No? This is the flat surface. This is just for the possibility that you can measure the blades also, you can the.
I just didn't understood.
Huh.
This is the blade profile,
Mm-hmm.
and the holes what you have approximately,
Mm-hmm.
where you have placed it.
Actually I have not done a study on the blades, so I have just put it this picture for the that sample that you can put the blade analysis, but based on my experience I can say you need all around the blade. Blade means all around the blade you will put the hole, means the performance will be different on the pressure and suction side.
And what you have shown is for only plates.
Only flat plate and corrugated plate. Basically our aim was to investigate the afterburner of aero engine, so there only the corrugated surfaces are mainly used.
Exit power,
No, afterburner, as you can see. Oh, I need to go back. This is the afterburner. This there you can see. This portion we are actually focusing.
Okay.
Yeah, no. We have calibrated our thermocouple before using to the air can. Yeah.
That is what I am asking. The process, how you have calibrated, so that is.
Okay, process. So first we calibrated our thermocouple. So we use basically based on the temperature range. So our temperature range was close to the 60. So we use the T-type thermocouple. So these thermocouples are basically hole inside the plate. The plate was basically the nylon plate, and that plate, the based on the there is a glue which is called the what we call it as non-thermally conductive glue. So with the help of that glue, we just inserted the through a pinhole. We inserted the thermocouples, and we focused the air camera also on the through the air window, and we recorded the temperature, and we measure the thermocouple temperature also. And based on that, this is the comparison we have done.
I think what was the exposure time for this IR camera? So is it instantaneous temperature or it's a steady state temperature?
Once system is reached to the quasi-static conditions, then we started our recordings.
Then, in that case, that much of deviation should not arise, because if both are at steady state, then their temperatures should really match.
No, deviation will come because thermocouple will have some error, right, or uncertainty. Air camera also have some uncertainty that will come. Actually we are measuring in the flow, so in that way deviation will come. You are not.
That is why I asked.
Yeah.
Is it instantaneous temperature?
No, actually in the flow field, no? So there will be chances of difference, like in if you are measuring in a steady wall or somewhere, so there will be exactly the same temperature you will get. Like in the boiling case, we have measured using the both of the air camera, and that you can say there is difference hardly less than 1 degree.
The plate, what you have chosen, have you
Have you placed it? It's a post-flow condition or it's a natural flow kind of thing? You have done some experiment, I think.
We placed our, like, this is the setup actually. So you can say the plate was kept like this, and in that plate we injecting the coolant through that.
Post-flow condition.
Yeah,
Post-flow condition.
and the main stream is flowing, which is the heated air.
Thank you.
Can you go to, I think it was slide number 2. Oh no, this one, 4.
Hmm.
4. Is it this plot from literature?
Yes.
Yeah, because the unit is not correct. So degree Kelvin is not a unit.
Yeah.
And the temperature you are showing here, this is the temperature without cooling.
Yeah, without cooling.
Yeah, so okay, so the need for cooling. Then I think it was slide number 6.
Yeah.
So you show here the injection angle.
Mm-hmm.
How is it defined? So
It's the angle between the main stream and the secondary stream measured with reference to the plate.
yeah, at which position?
Yeah, position is, this is for the flat plate actually. So position is that we have a lot of the holes.
Because
Means,
this is the angle. So on the right we can see it maybe better between the counter-rotating vortex and the surface. So at which position in this counter-rotating vortex are you measuring? In the center, at the bottom, at the top?
basically this is the counter rotating box appearing this.
Yeah, but how would you define the injection angle?
Ejection angle.
Yeah.
So this is the angle between the, this is the main stream flow directions,
yeah.
and this is parallel to the flat plate, and this is the secondary flow direction. So this is angle between these two actually.
Okay, it's on this line.
Yeah.
So that means if you change the
Injection position.
the angle of the nozzle, it would also change this injection angle.
Yeah,
Yes,
if we change the secondary stream position, means angle we change, then the penetration will change.
And how is this? On the next slide, you have shown the variation of the inlet, the shape of the inlet.
Yeah, this one.
Does this not also very strongly influence the, not the injection angle, but the mixing at least?
Yes.
Yeah.
But there was significant reduction in the strength of the material, so that was actually absolute after some time. So it was the beginning of phase of the film cooling basically.
Can you go to slide number 10, please? So here again the unit.
Oh.
The unit is 0 degrees Celsius. What does it mean?
Oh, that is wrong actually.
Yeah, so the unit is degrees Celsius.
Yeah.
So why we have this 0 degrees Celsius?
No, this is not 0. This is a error actually.
Yeah, because on the next slide you have also used this. Maybe can you continue?
Yeah.
So flow without heat transfer means you have not used not heated air.
Yeah, we are not using the heated air.
So you see, you have done this experiment in not in Germany. So we seldom have 30 degrees Celsius ambient temperature.
Yeah.
So it's warmer here in India than in Germany.
Yeah, we have done index experiment at Manipur actually.
Yeah. So what is the maximum temperature of the heated air you can reach?
Actually, through our heater, we will be able to heat 62 degrees centigrade.
Mm-hmm. So when you then look at your slide number 4, where you have talked about temperature of 2000 something Kelvin,
yeah.
How can you compare your results with the conditions in an afterburner?
Actually, for the validation, we have used just this experiment, and numerically for the parametric study, we are going for the high pressure and temperature. Once we validate the model, then we go for the higher.
So you want to use these ambient condition experiment to optimize your numerical setup and to validate
Yeah,
this. Okay.
at low, basically low density ratio.
Yeah. Can you show please slide number 11 again? You have here Mach number 0.5 and 0.
This is blowing ratio actually. This is blowing ratio. This is a similar kind of thing, that is blowing ratio. In film cooling, it is the ratio of secondary steam mass flux to the main stream mass flux.
So when we have so in second case you have higher secondary mass flow than on
No.
the left.
M is 1 means the both secondary and main stream. Comparing to this case, this case have higher flux, secondary flux.
Yeah, but the cooling is not so good. So you have more secondary flux, more cooling flux, but the temperature is higher.
Yeah. Because at a high blowing ratio, generally the lift off, actually the stream is lifted, secondary steam is lifted from the surface. That is the main issue with the higher blowing ratio. At low blowing ratio, it will be remain attached to the surface. Once you increase, it will directly penetrate and behave like a jet.
Is this then represented by M equal 1?
Yes?
Yeah.
It has already been discussed in many of the literature actually, that at high blowing ratio, it's penetrate into the main stream.
Yeah, but this high blowing ratio is this then represented by this M equal 1?
Yes, yes.
You said this is the ratio of
Yeah.
primary and then secondary. So if we have a very low primary flow and a very
It depends upon the hole shape actually. Suppose we are using the shaped hole, so in that case at m is equal to 1 there will be no lift up from the surface. If you are using the shaped hole, diverge hole. But if you are using the cylindrical hole, after 0.9 or something, they start means many of the previous researchers have reported, like Goldstein and others have reported.
This I understand. The question is then the separation, so you don't have gives the blow ratio here.
It's
This maybe the more important
means
quantity.
blowing ratio. This case is given 0.5 and other case is 1. 1 means I think you are thinking like that, it's both are equals, then how can be possible to means lift up from the surface, I guess.
Why the cooling is not so good, and the explanation is you have lift off.
Yeah. So for better cooling, the attachment is required, better detachment from the surface.
Yeah, but so if you reduce both velocities,
Mhm.
you also have m equal 1.
Yes.
But then you don't have any lift off. Or?
Yeah, in that case means there is a balance between the density ratio and the blowing ratio.
Yeah.
So there is optimum value at which the jet will be completely stick to the surface. Otherwise, it will be lift up from the surface.
Yeah. Now, therefore, the question isn't. So I don't see any information about the blowing ratio here,
Yeah,
or the velocity, flow velocity.
which case? Only we have given the blowing ratio information here, and we have defined in the beginning itself.
Then you have these CFD results.
Yeah,
The
yeah.
2D plots. Can
Yeah.
you please show it again? No, yeah,
This one?
this one.
Yeah,
When we look at the right at 0.5,
yeah.
mm,
Which one? A, B, C, D.
so there is a white triangle between the red flow.
This one?
No, it's at the above here on the right.
This one.
Yeah, and then the other graph.
Actually, we are presenting the non-dimensional temperature, which is generally opposite to the in calculations. Like in film cooling, it's like temperature. So temperature is is opposite to the film cooling effectiveness representation. So higher the film cooling means it will be in terms of the non-dimensional temperature. It will appear like red colors.
Okay. So one final question. We have shown also some examination of the thermal stress.
Yeah.
So are you working here together with an institute specialized for material science, or how do you want to use this data?
Actually, we are getting some of the CFD result, so temperature profile, and the selected domains, and we are just using the temperature what we are obtaining through the CFD. And before CFD we did some experimental to validate the CFD methodology. After that, whatever we are getting through the CFD, we are just using the temperature profile for the specified material which is mainly used for the afterburner, like Inconel 738, and using their property of Inconel 738 and using the temperature profile boundary condition, we are trying to calculate the thermal stress.
Yeah, and so for what do you need this? What is then the usage of this thermal stress? Do you want to change the material, or to optimize the material, or is it just an additional information?
So, and what we got actually, that in case of reverse ejection, the cooling is more uniform. So we are trying to show that in reverse ejection the cooling is more uniform, and because of that there is a significant reduction in the thermal stress. So the life of the component will be more if we are doing the means reverse ejections. So basically the ultimate aim is to protect the component. So in that way it is better actually.